this point? Okay, this should be in the previous one as well. So the conjugate base of the carboxylate is better stabilized due to resonance, right? So this is more acidic than the alcohol, okay? You remember Henderson-Hasselbalch? That's too long ago, right? So Henderson-Hasselbalch equals pKa plus log of conjugate base concentration. Okay. Now, physiological pH, what does that mean? That's in our system. Okay. What's the blood buffer range? It's between 7.35 and 4.5. Okay. So buffers are very important in, so you learn more about them in biochemistry. The ratio of the carboxylate ion corresponding to the acid is 1,000 to 1. Okay, so they're talking about this ratio. And this is the carbonic acid. Okay, so when we inhale, when there is, when we have the carbon dioxide in the system reacts with water to form carbonic acid. So that's the acidic component of the buffer in our system. Okay, so this is one. And then there is another buffer system, and that's the phosphate buffer. So both of these help control the pH of blood. Okay. Now this is this is another acid, carboxylate ions, and the vital rows. Okay, 25. That's, you'll be studying that in biochem. And here pyruvic acid forms pyruvate. I don't know if you have studied these before. And I do not know too much about how it reacts in the system. Okay. Now, remember ARIO, atom, resonance, induction, orbital. So resonance, we can compare carboxylic acids with something else. But among carboxylic acids, we can look at induction. Look at these different types of acids. This has a CH3 here, and this is CH2, with a chlorine, 2 chlorine, and 3. Now, if I asked, arrange these in order of increasing acidity, how will you do that? What's the first step? When I ask a question like this, what's the first step?
You draw the conjugate bases.
That's right. It's as simple as that. And we'll fetch you 2 points out of 6. I know it's time consuming. Okay. What's the next step? What's the next step? Using REO. To identify the stability of the conjugate bases, right? So now, how will you explain this part? Well, we know it's not resonance because there's resonance everywhere in all of them. So it's inductive effect. What do you know about Cl? Cl is, what is it?
Doesn't it destabilize it?
Destabilizes it, is an electron withdrawing group. How does it destabilize it, Adele?
Because it pulls electrons towards it.
Okay, so that's right. It pulls Cl pulls electron density from the oxygen towards it. Okay, that part is right. So will this, so this causes delocalization. Terms causes delocalization. Causes delocalization. So then the question is stability increased or decreased? Because,
Well, I guess it would be increased because the more stable the base is, the more acidic the acid is.
okay, so you're going backwards now. You're looking at the pKa values, right? So causes delocalization. This stabilizes conjugate base. Okay, so look at a case here. I'm just going to make it simple. All right, so this will pull it towards itself. This, there's no pull. So this we call delocalized. When we say delocalized, that the electrons are not there for an H plus to come grab it. When H plus comes, he says, no electrons available or less electrons available. Okay, remember, if the package is not there at the doorstep, then the mailman cannot have it. So the H plus bonds with the oxygen through the electrons to form the acid. But if the electrons are not there, then he's not going to make the acid. In this case, if an H plus comes, he's like, oh, electrons are there. You'll understand, you need to think about it. And then your thoughts then will transfer better on paper. Understood? I want clear explanation on the exam. That's why I'm going through this process again.
So what you're, I think, I never, I never grasped
ahead.
this part, but you're saying the inductive effect, it like pulls the hydrogens closer so they're not there to,
Say that again. I'm not understanding.
are you saying the inductive effect, like the chlorine atoms, they're like pulling the hydrogens close to it so they're not available?
They're pulling the electrons of the oxygen
Okay.
away from the oxygen. So if you think about the reverse reaction, this is the reverse reaction, right?
Yeah.
So if the electrons are not there, then this H plus cannot form that acid back.
Okay.
You understand? So it'll remain this.
Okay.
And therefore, this is a strong acid. You got to think a strong acid gives away its H plus readily, right?
Mm-hmm.
Why? Because it forms a conjugate base like this, and it does not allow the H plus to react with it to reform this. Are you understanding?
Mm-hmm.
Yes, no?
Yes.
Okay. Any other questions? But if it is localized,
Then it can easily form.
yeah, then that acid is not going to be a strong acid, okay? So you have to look at it in full circle. Anybody else have questions? Because we're going to look at this quite a bit here and also in 22.
So the more chlorines that are added, the more delocalized it will be.
Yes, yes. So the more chlorines added, more Cl atoms in the conjugate base, the more delocalized the electron density. Okay. When it comes to this, the The mailman does not see any trace of the electrons. See that? So stability increases. Stability of the conjugate base increases as you add more electron withdrawing groups. So now going back to this, now you can tell me, right? Do you get that? Which will be the strongest acid here? This guy. Let me see if I have pKa values. Okay. This is 4.74 or 4.8. Okay, that's acetic acid. This decreases to 2.9. This decreases to 1.3. This is 0.9. See that? So although it's an organic acid, its pKa decreases considerably with the electron withdrawing groups. Now, if you had fluorine here, it would be even lower than that. Now, tell me, all right, got this part? Understood? Because we're going to look at more examples and then I'm going to assume you know this part. Now, I'm going to ask you a question. Compare this with this. Will this pKa be higher or lower than 2.9? And
It will
why?
be higher.
What does higher mean? More acidic or less acidic?
It'll be more acidic.
What?
Less.
So, lower the pKa, Adele. Lower the pKa. What? Higher the acid or higher the acidity or lower the acidity?
If it has a higher pKa, it'll be a lower acidity.
Yeah, okay. So then, this is 2.9. Will the pKa of this be higher or lower?
So it'll be lower.
It'll be more acidic,
Lower.
you're saying? You're saying
Yeah.
it'll be more acidic?
Yeah.
Okay. Anybody else? John?
Well, it should be more basic, right? Because the chlorine's gonna be further away.
So you're saying the pKa should be higher than 2.9?
Yes.
Yes, okay, yeah. So you're saying this should be less acidic then,
Yes.
isn't that right? It's hard with the pKa values to get it. Okay, so you have this conjugate base. And then I have the other one. Okay, this is alpha carbon. This is beta. And your Cl is here. Which will be more stable? Which will have a greater pull on the electrons? Which which will effectively delocalize the electron density?
Left side.
This will be more effective. In delocalizing the electron density on the oxygen, on the O minus. So if this is more effective, why is it more effective? You can be more effective when you are, Jamie?
Closer.
Yeah. The Cl is in the alpha position to the carboxylate ion. So if you're closer, you are more effective, okay, in delocalizing. So this is less effective. So inductive effect usually decreases as you go farther from the site of reactivity. Inductive effect fades as the is farther from the O minus ion. Got it? So now, this pKa is 4.1. So it is considerably higher than the other one. And look at this one. This is alpha, this is beta, this is gamma. So what would this be? Slightly higher. It's not a whole lot higher. Okay. So the electron withdrawing group is most effective when it's at the alpha carbon. And we have another group of acids to look at. Any questions so far? Okay. I want the explanations to be clear. Whether it's homework or test. All right. Now we are looking at benzoic acid. And I'm going to go ahead and draw the conjugate base. Now you should know for this as well, the type of activating group it is. Whether it's a weak activator, strong activator, moderate activator, not necessarily for this part, not necessarily if it's OP or otherwise. So I'm going to pick 3 examples. I have the NO2. What type is it? NO2. We cannot forget that. We need that for the test. What is NO2?
Nitro.
Strong deactivator.
Strong deactivator. What about OH?
Strong activator.
Yeah.
Strong activator.
Very good. And then I'm going to choose hydrogen to be neutral. Okay. So now this is deactivator. Then I'm going to look at hydrogen. Okay. So now, how does each of these affect the stability of the three? Which one do you think will be most stable of the three? Label these as 1, 2, and 3.
Number 3.
Number 3 will be the most stable.
Hold up.
Okay, let me ask you this.
Number 2.
The middle? Which conjugate base will be the most will have the most delocalized electron density?
The first one.
Which one will have the most delocalized electron density?
The first one.
Why is it the first one?
The nitrogen.
That's right. Okay, so this is like your electron withdrawing group.
Oh, Dr. Mary, it
So
just
this-
reminded me.
Huh?
I had a question. It's been on our homework assignments and like our quiz.
Yeah.
So regarding the activating groups,
Mhm.
I usually run into that question, which one is the most reactive? I usually just put alcohol, but I really don't know like which one.
You have to go, there's a chart in chapter 18.
Okay.
So, and it's ranked by strong activator. So you have to know that for this one as well.
Okay.
So the strong activator, then moderate activator, weak activator, weak deactivator.
Yeah, but how do you go like if you get like a nitrobenzene and an alcohol?
Yeah, so the alcohol is here. So the nitrobenzene is here. So reactivity increases this way.
Okay.
Does that help?
Yeah.
All right, so now coming back, which will be the most stable conjugate base? So the one that has the strong deactivator is the most delocalized. Oh, I guess you can't read that much. And the most stable. Okay, so this guy is like an electron donating group. Here's the electrons, right? You can use this to draw resonance structures inside the ring. So he's actually pumping electrons the other way. So this is the most localized, has the most localized electron density. And hydrogen is in between, okay? So it's in between. So this is the least stable. So which one will be most acidic? Nitrobenzoic acid or hydroxybenzoic acid?
Hydroxybenzoic acid.
Will be more acidic?
Yeah, than the nitro.
Okay, now I'm going home. I'm
Oh,
already
wait, no,
home.
never mind. Yeah,
I said I was going home, Adele, but I'm already home. What is it?
the nitrobenzene because it makes a more stable conjugate base.
Okay. All right, good. Okay, so the corresponding acid, look at the numbers up on top. This is the most acidic because in the list here, this is the strongest deactivator. This is moderate. This is weak deactivator. This is neutral. This is weakly activating. This is strongly activating. There's no moderate here, but we can add it. You see that? So the trend in terms of acidity is this, okay? For electrophilic substitution, okay? Reactivity increases upward. Going up, all right? But for acidity, it is in this direction. The more electron withdrawing substituents or more powerful substituents will increase acidity of the benzoic acid. All right. Now, when we get to the amines chapter, instead of this, we'll have an NH2 group. And then we'll look at similar trends. Okay. So we've looked at different aspects of the acidic nature of carboxylic acids. They are acids, so they should be acidic. But how is it affected by different substituents? I'm trying to look at the time. Okay. Okay, now we're going to more reactions and stuff. So I'm going to move on unless you have any questions. Now this is, it's not very clear. These are reactions that you've seen before where acids are produced. Okay, I'm going to write the first one down and use another sheet of paper. Remember ozonolysis, water? What will it do? It makes two acid molecules. Okay, and that's chapter 9. And then we've looked at oxidation reactions. Primary alcohols. You know the reagents. Okay. Sodium dichromate, sulfuric acid, water. And this is chapter 12. Okay. You should still know these reactions. And then more recently, we saw okay, if you have a benzylic hydrogen, oxidation will take out all of the attachments but leave a carbon, which is a carboxylic carbon. This is 17,6. So you have to know these reactions is what they're saying. And then we have two more reactions that we're going to learn here. One I've already talked about. Okay, so you have 3 methods to make the acid. Okay, 3 methods to make the acid. Now, this is a nitrile. Remember cyanohydrin reaction? Hydrolysis. This is acid hydrolysis. Okay. The reaction is warmed up. This gives you acetic acid. Now, how do you make this nitrile? Cyanide, this is a nucleophile. It's a good nucleophile. Okay. So this is SN2. Br minus. And then you can treat this okay. The nitrogen will leave as N2 gas ultimately.
Dr. Mary, are you missing one carbon?
CH2CN. Yeah. Thank you. So there is. Yeah. That's why it's primary also. Well, it's actually benzylic CH2. Thank you. All right, so you need to remember this. This is very useful for synthesis and stuff like that. Because anywhere you want a carboxylic acid, even in chapter 18, you can use this reaction. Another one you're familiar with. So if you need, this is from the Grignard reaction, right? Minus. And then you add and you get a tertiary alcohol, right? So this is a Grignard reaction that you're familiar with. So if you need a tertiary alcohol, you use a ketone. Ketone gives you tertiary alcohol. But if you want a carboxylic acid, then you use CO2. One carbonyl is converted to the OH group. The other carbonyl is retained. Isn't that amazing? I think so. See that? That's clever. And I'm surprised that it worked too. You know why that's oxygen is far away. And then you work it up with water, or they could even use acetic I think for this you need H3O plus because it's an acid, not just water. All right, so it's similar to what you've seen, but here your reactant is carbon dioxide and not an aldehyde or a ketone. So this is putting everything together. What is this? Diethyl ether. Okay, so you have the Grignard reagent. And then first step is CO2. H3O plus, okay? Benzoic acid. It's amazing. I'm amazed, as always. Okay, trying to see what's the next one. Got that? So Grignard reagent, reaction to prepare benzoic acid. One is with CN minus, and two is with CO2. Grignard. Okay. Now, reactions of carboxylic acids. So we're going backwards. You have the carboxylic acid. What is its reaction with lithium aluminum hydride? Let's follow this. This is LaH. Okay. The carboxylate ion is formed. Okay. These two form H2 gas. Okay, the rest of it is in the next page. So I'm going to show the final product. This is reduced to a primary alcohol. Okay. Look at all the changes that happen. But it doesn't go directly to the primary alcohol. What would it form before it forms the primary alcohol? Anybody? You know about the oxidation of primary alcohols? Do you? What would it form? How'd she remember?
An aldehyde?
Aldehyde, yes. So we are going to convert this to an aldehyde. And then to a primary alcohol. Okay. So we've only gotten up to the carboxylate ion. Okay, acid. So we're going to see how it becomes an aldehyde, and from that, you know, you've seen the mechanism before. So let's look at the steps. So remember, ALH3 is formed. So this is like our 2+2 cycloaddition. All the changes. You don't have to know the mechanism for this one. So this folds in, that leaves, and ultimately you get an aldehyde. Aldehyde. And then from an aldehyde, you know this one. And it's converted to a primary alcohol. Okay, I'm going to say here, show mechanism. And I'm going to ask you to be responsive. Huh?
I have a question.
Yeah.
Are this reactions
Hmm.
performed in two different steps? Like, is the aldehyde isolated first and then treated again with LaH, or is it just the same?
Does it go continuously? I think it is, it could be reactive enough. So it can happen in the same pot, in the same,
Right. So
stuff.
whenever we form the aldehyde, it's just that another LA,
and another molecule of LAH that
comes.
will, yes, because that guy's reactive, so you don't have to separate it out. He'll take it to it'll be taken to the primary alcohol state. Yeah, good question. Okay, so use another molecule. Of LAH. Okay. Now there's a way to stop it at the aldehyde. We'll be looking at it a little, a couple of slides later. Now remember our BH3 THF? This was used for hydroboration. We're going to use it again here. This is very interesting again. CH2, he also reduces this to an alcohol. So here, sodium borohydride, remember, he's not effective in reducing acids or esters, only LAH. But instead of sodium borohydride, along with LAH, you can use BH3-THF. And it does the same thing. But then he is a little finicky. He will only reduce the acid and not the ester. Here's a typical example. So this is Kiva selectivity. So what does that mean? If you use BH3, you have an ester here and an acid here. What does he do? He's one step above NaBH4. He makes this into a primary alcohol, but he's like, okay, I'm not going to touch you, ester. Okay, a lot of theory to go into the
Dr.
detail.
Marie, can you move it down a little bit?
Okay, this one?
Yeah, thanks.
Okay. We got 20 minutes. Got it, everybody? Next section. Carboxylic acid derivatives. Just a second, it's Dr. Dees. Hello? Okay, 2 chat questions. One. Oh, y'all are answering. I should probably look at that too. Okay. Sorry about that. He had a Zoom question. The reduction of carboxylic acids. What was he saying? The acid, has its own reactions. And then from the acid, one of the derivatives that you've looked at is the ester. And then you have the amide, and then you have the anhydride, and you have the acid chloride. We'll only be looking at the ester we look at the mechanism for the making of the ester because you did it in lab. Okay. Now, if you go from this, where you have an OH, to a carboxylic acid derivative, okay? This could be something like Cl, or you can make it into an ester, okay? Those are carboxylic acid derivatives. There's no change in oxidation state at this carbon when you do that. But when you go from an acid to an alcohol or an aldehyde, there is a change in oxidation state. Okay, that is reduction. But with the carboxylic acid derivatives, what they are saying is that there's no change in oxidation state. Okay, they're just making a statement there. The reactivity in terms of oxidation number doesn't change at the carbonyls carbon. So what are the different derivatives? At least we need to know what they are. This is the acid halide. Okay, you have a Cl there. You've used this before. You remember for which lab? The acid anhydride. One of the labs. You used acetic anhydride. And this is ester. And this is an amide. Okay. And this is the nitrile. This is also a derivative, although it doesn't have the carbonyl carbon. Okay, no carbonyl carbon. Acetic anhydride, you use that to make aspirin. Remember, salicylic acid and acetic anhydride. Okay. Now we'll talk about esters. Are relatively unstable. Okay, acid halides and anhydrides are not common and naturally occurring compounds. But esters, okay, that's the fun part. This gives you the pineapple flavor. Okay, when we talk about flavoring, this is what is used. This is banana. This is what that's your lab. And butyl acetate smells like pears. Just some common examples. And then, of course, our derivatives, the proteins. You see that you have the amide structure. I don't know what you call that. Well, it is the amide structure in biochem as well. And then you can have melatonin has the amide, okay, among other things. So your protein structure, though, the link is the amide link. Okay, here, this is the most reactive in a chemical reaction. And all of these are delta plus, right? Electrophilic. And reactivity is determined by induction, resonance, sterics, and quality of leaving group. So we're just skimming through this. So the most reactive is the acid halide. The least reactive is the amide. At least you should be able to recognize these structures, be able to give the formula for the functional group, and not discuss really, but be able to say which is more reactive and which is less reactive. I think they're looking at the topmost case and the bottom case. These are the most reactive. And one, because if you look at the structure, you have it's an electron withdrawing group, right? This is delta plus, this is delta minus. So as it is, the carbon has less electron density, and this guy is pulling away whatever he can. Okay. So this carbon becomes more electrophilic. Okay. The chlorine atom does not donate much electron density to the carbonyl carbon. So if you look at resonance, I can draw another structure. Now, chlorine with a positive charge does not make it very stable. Okay, so that's why it says it does not contribute much electron density to the carbonyl carbon. Chlorine is not going to have a positive charge. Okay. But because of these two factors, you see the carbon has a positive charge here, and the delta plus is enhanced because of the presence of chlorine. So the acid chlorides are therefore the most reactive. This is the most electrophilic among the derivatives. That's what they're trying to say. Now, the one that is least reactive okay, this is less electronegative than chlorine or oxygen, is not made more electrophilic. Okay, for the reaction to take place, that that carbon must be very electrophilic for a nucleophile to come and attack. But if the surrounding factors do not make it more positive, then reaction is not going to take place. So we can do the same thing here. Positive charge. But nitrogen being less electronegative will be okay carrying a positive charge in the resonance structure. Okay, so I'm going to say carries it better than, carries the positive charge better than Cl. So this is okay. But what does it do? Makes the carbon less electrophilic. A lot of theory today. Couple more minutes. I want to start the next. It's just a continuation of this section. Okay, so we are only looking at why the acid chloride is the best, and or in terms of reactivity, and why the amides are the least reactive. So you should be able to explain it using the two factors that we've considered. Okay, so what is so different about these? Let's see what we have going on. Okay. Aldehydes and ketones, they are also electrophilic, right? Carbon delta plus. These two undergo nucleophilic, that's chapter 19, addition. All right, changes, subtle changes, not subtle, it's different. These though, this is also delta plus, these undergo nucleophilic acyl substitution. So what happens here? this guy leaves. Okay. In the case of aldehydes and ketones, you have the nucleophile coming in, but changes are made here. An addition takes place. In this case, the carbonyl is retained and the Z group leaves. So this is substitution, and the carbonyl group is retained. So you have to know the changes. Okay, how is it different? Got it? So, genetic mechanism, 2 core steps. Nucleophile attacks. Right? Now this forms a tetrahedral intermediate. See, this is sp2, right? sp2 hybridized. This is sp3, but it's an intermediate, so it doesn't last very long. Now the carbonyl is reformed, but then this guy should be a good leaving group. Okay, that's another reason why these halides are good for these reactions, because they are good leaving groups. So then you get your structure back. Right? sp2, you have the carbonyl, and instead of the Z group, you have the nucleophile. Now they're saying with aldehydes and ketones, these are not good leaving groups. Okay, not good leaving groups. Therefore, they undergo addition and not substitution. Okay, a big reason why that undergoes nucleophilic addition, and this cannot undergo nucleophilic substitution. I'm just going to show a specific example, and then we're going to stop there. I think on Friday after the test, we will look at the mechanism for esters. So it'll only be about esters. So here, nucleophilic attack. Okay, same as what we saw. And then loss of leaving group. This is a good leaving group. And we have an ester here. Oh, they're showing it here. Okay, it must take place in these steps. So there should be a first step and then a second step. You cannot have an SN2 type reaction. You cannot have this and that, okay? Not an SN2. So it must be nucleophilic, attack first, and then there's proof, for the mechanism, and then loss of proof. With that, I'm going to stop. So what we've seen is, first of all, the acidic properties and how to explain. And then once you know how to do this, then when I do the amines, then it'll click better because there are changes. Okay, this is acidic, that's going to be basic. And then we saw some methods to prepare the acid, and then some reactions of the acid, and then we looked at acid derivatives. You should be able to name them all and know the trend of reactivity, and also explain why acid halides are the most reactive and the amides are the least reactive. And then be able to do simple nucleophilic acyl substitution reactions. And then on Friday after the quiz, I'll look at esters, and then look at amines. And if I'm not able to finish the amines, then after your quiz on Monday, I'll take up a little bit of time to do that, but we'll have to see how we do it all, okay? We'll just concentrate on Friday for now. And then I will be posting a homework for 19, which will be reactions. Since you're doing all the mechanisms, you're studying for the mechanisms. And then I'll be posting one for 20 as well. Okay, so you can start reviewing. And I will also start thinking about how to do the sapling for chapters 12 through 16. So we'll talk about all those things on Friday. Okay. And I know you're busy this week as well with other tests, so concentrate, and you got just one more week left, and do the best you can. Any questions as we wrap up? No, brain is fried a little. Okay. All right, take care, and I'll see you Friday at 12. Okay, be safe and take care. I'll stop recording for